So I'm grading your tests. Actually, I'm grading I'm almost, well, probably be done later on tonight with the classroom set here, papers. And some of you turn in papers, so those get graded first. And then I'll grade the my iPad version of your test that you sent in. So that will be maybe tonight. It might be tomorrow, but it'll get back to you by tomorrow, say late afternoon at the latest. All right. And then you'll have till Friday midnight to resubmit your blue work. Moment of truth. Yeah, all right, good. So we're in business. Let's see who we got. Okay. We got the usual crew. All right, here we are. We're at class 19. And we are down to nine more sessions. That's it. Who is this? This is the question. Who is this lady? This is your new principal. That is Hallie Wright. And Hallie used to be a teacher at Norman High back in 97. 96, 97 range. She taught business, marketing. I didn't really know her very well. I was in the science building. She's in the main building, but I knew of her. And so she then went off to Putnam City to be not a counselor, an assistant principal. So she's been in Putnam City for many years. I don't know, 15 or so. So she'll be our principal next year. She'll probably head over here pretty soon, and then she'll start in June. And if you're a junior or a sophomore, she'll be your principal next year. Seems all right to me. I did get a student to do the meme for this versus this. It's the same picture. It's the same meme, just the same situation, just redrawn arrows. And a lot of people didn't realize that. Well, a lot of people, let's say maybe 6 or 7 or 8 students didn't realize that, and their free body diagrams got nothing to do with their head and tail. So it's the same arrows, just rearranged. In class, I showed a little bit of the video of, it's on Facebook, so I'll let you guys watch it on Facebook, but of Ollie going to the Devon Tower to go on Oklahoma's fastest elevator, and it accelerates the fastest. So it goes from 0 to 49 floors really fast in a matter of less than a minute, I think. So that's pretty fast. But he's looking at his weight, and we're basically looking at the elevator equation. So it's room for improvement. I mean, it's a good start. I gave him 10 stamps. It's a good start, but I couldn't read the numbers off his scale. So if somebody goes again to do it, focus in on your analog numbers on the meter and show me where the needle's going. Because he says, well, I lost 30 pounds, I gained 30 pounds. But that's a lot, because 20 pounds is what typical elevator you'll gain or lose. And it's a percentage of your weight. But for someone like me, and he's about my mass, you want to lose about 20 pounds. So 30 pounds seems a lot to me, but that seems almost uncomfortable. But that's what he said, and so I'll go with it. But I'd like somebody to go back and focus in on the needle, maybe some this weekend or something, and film it. And I'll give you that 10 stamps equates to 30 points. So we'll see what he did, and then try and improve, right? But he did blaze a trail. First one to ever actually go there and do it. We were going to meet table 4, but then the first hour student that's there wasn't there. So I said, okay, we'll just postpone until Thursday. So we'll meet one of you, whoever I haven't met. I'll meet one of you on Thursday with the recording off. Went around today. Check 6, 7 are the false statements. You got to make them true. So went around and checked those. We're up to 29 stamps. Tonight there's like 1, 2, 3, 4, almost 5. You get up to 5 stamps tonight. So it puts it at 34. We're getting almost at 40. Stamps doesn't mean much to you except that it's points you're going to get on the next paper, which will be probably 6-4. It could end up being 6-6, 6-4, 6-6. Those are the two that I'm looking at, either one or both. All right, let's look at this. We did this in class. Let's look at these false statements and show why they're false. So 1, it says a rocket moves through space because the exhaust from the rocket's engine pushes against the atmosphere. Who says that's obviously false, but what's false about it?
There's no atmosphere in space.
No atmosphere in space. So right there. So if I'm swimming in a pool, I'm pushing against the water pushes back on me, right? And that's how I propel through the water. But and to a certain extent, same thing with like a prop through our atmosphere. But through space, the rocket has to bring its own atmosphere with it, which it shoots out the back. So that's basically a Newton's third law, a recoil situation where it's m dot, right? M dot VE, it's shooting particles out the back, and so it could go anywhere. It doesn't need atmosphere. Number 2, if an unbalanced force in opposition to the motion of an object were applied for a sufficiently long time, the inertia of the object would reach 0. What say you? False, but why? And all these statements, glancing at them, they seem, that seems logical, seems smart. That must be right. But they're all false. What's wrong with this one?
I mean, the idea is that inertia keeps stuff moving, right? So it would have to, for it to be moving, it would have to be more than 0. I mean,
yeah, inertia is a bad word here because inertia is the mass of the object. Well, putting a force, unbalanced force on an object is not going to change its mass. Well, okay, if it goes towards the speed of light, it would, but on a typical, mechanics. So it doesn't. Maybe if you took out the word inertia and put in velocity, or assuming that you have a force that's slowing it down, or you put in acceleration or something, and you made it unbalanced negative force. Oh, it says in opposition. Okay, so yeah, so if you put in the word velocity or acceleration there, you'd be fine. Number three, we kind of skipped because we didn't really get a chance to do the inertial balance lab because of COVID. I cut that one. It's kind of a cool lab, but it's about oscillations and plotting. We kind of blew past that one. So skip that one. 4, according to Newton's third law of motion, if a small steel ball were thrown horizontally and bounced off the center of a large steel ball, which had been sitting motionless on a frictional surface, both balls would accelerate at the same rate, but in opposite directions after the impact. What do you think?
It wouldn't be Wait, is it saying it would accelerate at the same rate as it was in the beginning before the collision?
Well, so yeah, I mean, it's all this statement's all messed up. I agree. The word accelerate, there's no such thing as conservation of acceleration. So they're not going to accelerate at the same rate. They're not the same mass, big ball, little ball. So yeah, you're right. And so you could say something about, well, the momentum. You could say both balls would blank at the same rate. You could say both balls would accelerate at different rates because they had different masses. But the momentum at the beginning, the mass times velocity, is the same as the combined momentum at the end. Something like that. But yeah, so the accelerate's the bad word there. Okay, now tonight, look over 6. We did 5 kind of together yesterday, but tonight, look over 6 and 7, and then we'll briefly talk about that conceptual thing. Okay, now in first hour today, so I'm going to assign this. I'll assign number 4 for homework as well. So the homework is This spend about a minute or two each on those. Those shouldn't take long at all. But then you can spend most of your time on number 4, and that is for 2 stamps. Well, not really stamps for you guys, but you'll get points because you've got to do 6-4 anyway. So I'm just pacing you out. So tonight's the night. We're going to work on 5 though the rest of this time. We'll spend the yeah.
So on number 4 is MN, is that meganewtons?
Meganewtons, yeah, capital M in meganewtons. So a million newtons per centimeter. And you have springs that are that strong to make a million newtons a centimeter. Just to squeeze it a centimeter takes a million newtons. Some of these truck springs for these semis are huge, high K values. And this is something that we won't get into until AP physics. We won't even get into, I don't think, no, we won't even get into this in June. And by the way, the website is live. Hold on. I show you, huh? So the website, www.askmelearning, you don't have to put the capitals in there. .org. Somebody, they came up with this askmelearning.com. Like they got our domain name. Like we stuck in .org at first because we thought, well, we're going to be nonprofit, and we are still going to do nonprofit stuff, but nonprofit's hard to do. Turns out it takes $2,000 just to start one because of all the forms. So anyway, so we're going with LLC for now, which normally you'd say .com, but askmelearning.com was taken coincidentally by somebody else, like at the same time. So they set this bogus little thing up. So I imagine sometime next year we're going to have to buy it off them, buy that domain. So go with askmelearning.org. But if you go there, it'll have Dr. Furnet's, as I showed you the post yesterday, it'll have Dr. Furnet's and his videos, and then it'll have Mike Ritchie and it'll have me. And if you want to sign up, now for me, it says it's $120, but for you, all you're going to do is sign up for the first week, and then the rest is going to be free because I'm trying to give you like a 75% discount because you're kind of guinea pigs. But I mean, I'm going to put a lot of effort into it. It is costing us money. We spent about $400 already. So trying to recoup some of our costs, but still trying to make it. Now theirs is full price because, they're not offering to their students. Anyway, so for my students anyway, it's 75% off. So just letting you know. But the question is, are we going to get into that? I don't know if we'll get that far. We are going to talk about Ultimate Fighting Tool. This is part of the Ultimate Fighting Tool, this 1FKX squared. And so I don't know if we'll get that far into it. Let's spend the rest of the time looking at number 5. 5 will work together, but 5, we did. I threw it out there in first hour. I said, hey, let's quickly knock this one off. And then as I determined pretty quick that we're not going to get through this real fast because students started having some questions. What the heck is this law? And this is, so in your cheat sheet, whatever, this is a top 5 relationships in the universe. One of the top 5 relationships. Not just on Earth, on any planet. And Newton came up with this one. This is called, okay. So now we're going to take some notes and we'll work the problem. But so don't start working the problem yet. Let's talk through a little bit. This is called Newton's law of, Newton's universal law of gravity. Being universal, meaning that it's true no matter where you go in the universe. The only thing I like about this course is that this is a truth. This is a true. This is how gravity. You'd say not how it works necessarily, but if you were to quantify it, this is true. That's what I like. It's not just this course. It's not just us talking here and that's a truth there or truth this year or next year. It's an eternal truth, and it's a truth everywhere. That's a pretty big deal. You're learning that kind of stuff. So this is how, and you go, how did Newton figure this out? He used data from Kepler. He didn't run an experiment because he didn't have the equipment for this. We'll get to that in a minute. So what the heck does this mean? Okay. Let's blow it up and look at it. Carve out some space here. All right. So each one of these, let's break it down. This is right up there with E is equal to MC squared, F equals MA, E equals H nu. All of these really important laws are fairly simple. You know, they're not like really complicated, but that's nature paints with a broad brush. Okay, this FG, this is the force between the attractive force. It's the attraction force between two masses. And it doesn't matter. It can be a planet and a moon. It could be a star and a planet. It could be me and you. It could be a gnat and a fly. If you have mass, this applies to you. Attraction force between so these two, so masses themselves. If I take this water bottle and this tape dispenser, they are attracted to each other simply because of their mass. If these are out in outer space and they're floating around, they may start to orbit each other, but eventually they're going to link up. Okay. And we'll talk about why that is here in a minute. Newton didn't understand why. At some point you say, well, that's God's, Newton was very religious, and Newton finally says, well, I mean, there are some things that only God knows. But he did understand how the relationship. All right. So let's get to the easy ones first. This is the mass. These are the two masses we're talking about. So mass one, mass two. Two masses that are going to be attracted to each other. This is how far apart they are. They're centers. Distance between centers. The centers of the object. And finally, we get to this G. G, put purple here. All right, G. This is called the universal gravitational constant. Universal gravitational constant. Now, every society in the universe, I don't know how you feel about UFOs, or there's a lot of talk lately about UFOs. I get it, they're unidentified flying objects, but I don't think they're aliens. But I think there are aliens. I think there are alien societies because we all have the same periodic table. And, there are now planets we're finding that are very Earth-like. I'm not saying you have to be Earth-like to have life, but the life as we know it. So on all of those societies, I don't know, what do you think? There's 100 of them, there's 1,000 of them. There is a theory recently come out that we are the leading technological society, Earth. We're it. We are leading it. Maybe others will catch up. Maybe they're in the Neanderthal stage right now, but they'll catch up with us perhaps. But that's a lot of pressure. We're the first. There's a group that scientists that say we are the first to start to explore the planets. And they cite their evidence, but anyway, so I'm going to assume though that we're not, that other societies are also at this point, at least at the point where they're starting to understand their, and they're, like I say, they all have the same pi we have, right? They have the same circles we have, the same diameters. Pi is simply the ratio of the circumference to the diameter. And at some points, they had their own, Pythagoreans and their own Greeks and Babylonians, and they figured out pi. So if we go to them and we say 3.1415, blah, 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 they're going to go, oh yeah, okay. This is assuming that they're using, the 10 digits. Maybe they're using 8, or maybe they're using 6 or something if they only have 3 fingers on each arm, whatever. But they have their pi. And in fact, I'm sure there's a little alien kid that can say pi out to 100 digits like we can. Okay. But this is something else they have, and it's right here. This G. They all have a G. A universal gravitational constant right here. This number. In fact, I know that pi, those kind of things are on Voyager. We put a plaque, on Voyager. I believe it was 1, maybe, and 2. But this is like, it's made of gold or gold plated, and it's out there now. It'll be the first thing that if they stop Voyager eventually, they'll look at, and they'll go, oh, I kind of wish they hadn't done it, because it's giving them a recipe for who we are, what we look like, what our number systems are, how much we know, music that we play. I don't necessarily want a alien race to know we exist, because there's just as good a chance that they're going to come harvest us or harvest our minerals as there is they want to come hang out with us. People think it's going to be a big, I kind of think not. I don't think it's going to go very well for us. Anyway,
probably shoot first.
I mean, that movie Contact, I love Contact. I love Carl Sagan, and I think it's awesome. But James Wood plays this character. He's very paranoid, and the older I get, I'm starting to become more like James Wood. Like, maybe we don't want to entertain them. I think there's a line in the movie that says, why would any alien race care about an anthill in Africa to come see us? And then someone said, yeah, what would we care about? If we see an anthill in Africa, we'll mow it down. We don't care. So maybe they don't give a rip about us. We think we're so special. Okay, so I got off on that topic, but this G, though, they have the same G. All right, so that's one of those universal constants. There's another one down here, right here. This is also a universal constant. We're not working this problem today, but this is Planck's constant, and this is universal. Everyone has this value as well. This is down to a quantum level, how things like it's the factor in E is equal to h nu, which is another one of the top 5 equations of mankind. Anyway, so back to this. We'll talk about that later. Yeah. So I wanted to talk about this G. This G is a weird number. And I had a student ask once, said, how did Newton in like 1700 come up with that number? Well, that was a fantastic question, because he didn't. I don't even know. I know he knew it was small, and he knew it. He looked at data from Kepler of planets. He didn't actually go out and do an experiment. And so from his calculations, and Kepler took very good data, he could come up with, I think he got it within a factor of 10. But to get this number, this came from the Cavendish experiment. And Cavendish experiment is one of the top 5 or top 10 experiments of all time. It put Cavendish on the map. Cavendish, like Cambridge experiment. It's around 1800, 1799, somewhere around there. where they went in, and this was the Large Hadron Collider of the time. They spent hundreds of thousands of dollars. I'm thinking we're talking $1,800. So in today's money, it's like it'd be $1 billion or $2 billion they're spending to come up with a way to get this number. Okay, so here's I got drawings of it right here. Here is their setup. Now, this wasn't this is a modern day setup. They didn't use a laser. They didn't have a laser in 1800, but they had another way of determining angle. So what you do here is you have this, and I have this hanging from my ceiling in my classroom. I have these red balls and these white balls hanging from the ceiling. I'm trying to give you a mock-up of it. But basically they have these two massive lead balls, spheres, that they had hanging, or they had sitting there. And then they had, this is one thing at two different positions. Then they had there's a quartz fiber that's holding this and a mirror up there. But then they had these other two balls that are free to rotate. Okay. And here's another example. So, whoops, I just picked these up today at lunch. So you have this suspended wire, you have these bar with two masses on the end. And then the idea is that because those big, heavy lead balls are attracting it, it will rotate. This guy will rotate because they're attracted. So really you go, well, that's fairly simple. The thing is, it had to be precise. Now today we can do this lab and we use a mirror. We have a laser. Okay. We point a laser in on this wire, or this cable, we hang it's like a fiber now, but we hang a mirror. And then when these very massive but smaller balls are attracted to the bigger balls, that causes a twist, and you see that the laser beam bounces off the mirror and then moves a little bit, and that little bit of movement is, you can work your way back and from there find out what G is. I watched this. Here's another view of it. I have some better pictures I'll put on the screenshots. This guy, okay, I applaud this guy. There's a famous YouTube, been around since 2013, and it's totally bogus. I mean, I applaud this. Is a teacher somewhere, a physics teacher, and I applaud him for trying, but come on. He has a couple of masses, a couple of kilograms taped to a meter stick. You can barely see it, but there's a string right there, comes up like this. And then he has two bowling balls. And so I think it's nice to show the kids that, but then he claims that time lapse over the thing is, it doesn't need hours and hours and hours. Gravity acts at the speed of light. So I think it's a physics teacher who doesn't really, there's a lot of physics teachers that don't really know their physics very well. So I think he's trying. I applaud him, for effort. And it's kind of cool. You can see it. But then he claims that this thing rotated. It's more the air currents in the room that caused it to rotate. And in fact, there's a disclaimer later on says, well, I think it was the air currents. But initially he said in his video, oh, well, look, see, after 12 hours, what? It doesn't need 12 hours. Anyway, misconception there. But people try and make, so I wanted to buy a experiment. I wanted to buy one so we could do it in class. Well, just the cheapest, crappiest version is $2,000. To get one that's really pretty accurate that you can actually get numbers out of, $10,000. So it's not cheap. So I just have some styrofoam balls hanging from the ceiling and just to show so I could point to something. Okay. So I'll put some more stuff about it in there, but that's important historically. Cavendish is huge, important. You have to understand what Cavendish was. And that put Cavendish Labs on the map, and Cavendish is still a big player in large experiments. But this was the Large Hadron Collider of the time. This was the experiment because, gravity is pretty important, and Newton had come up with a number. It wasn't that number. there, but he'd come up with a number. This number actually goes out a lot further than that. Usually you go about 3 siggies, 6.67, but it goes on and on. It's like pi. I think it does terminate, but we're limited as to how accurate we can make the Cavendish experiment. Okay, but also notice that look how small it is. That's why I can say that I'm attracted to you, and you're attracted to me, just our masses. But because that 10 to the negative 11th, you don't pick it up. You know, you don't. That makes everything so small. We're on the trillionths of a Newton dot meter squared over kilogram squared, and then also dig those crazy units. Newton dot meter squared per kilogram squared. Sometimes constants do have bizarro units, but the units have got to make the formula work, and that's what it does. Okay, so let's spend the next little bit of time trying to work this problem. This is real data. There's a exoplanet. When I wrote this problem, the hottest thing out there was Kepler 452b. The reason it's so important. Hey, somebody quickly Googled the mass of the Earth. We're on the 10 to the 24th kilograms, I thought. I think we're like 6 times 10 to the 24th kilograms, the Earth. And
it's 5.972 times 10 to the 24th kilograms.
Okay, thank you. So points there, a couple points for that. So we're about to 1 siggy. 6 times 10 to the 24th kilograms. That's the Earth's mass. Well, this mass is about over 10 times, maybe about 13 times the mass of the Earth. But it's a terrestrial planet, meaning it's not gas. It's in the Goldilocks zone from its star. It has, I think, 1 star. So the chances of it having life, now they're probably going to kick our butts, because this group has been dealing with 10 times the mass. So for them to be walking upright, if they can, they got some pretty strong muscles. I don't want to mess with these people. They're dealing with a lot more force than we are every day just to walk around. But it probably has some kind of life on it, right? I mean, I was doing a show of hands today. Let's do a show of your hands. How many of you think there is, okay, so hit the hand button. How many of you think that there is life beyond Earth out in the universe, that we're not the only, okay, so now, most people say yes. It could be amoebas, whatever, right? But now let's say, how many people think that the life out there is at least to the stage of fish and like crawly things, but maybe no societies, but at least you're at the stage of fish and or things that they may have methane oceans, but something that they have, like I say, they have the same periodic table we do. So carbon based. How many of you think that? But maybe they're not technological. How many think that there's life and it's complicated, it's multicellular, it's got proteins, but it's not intelligent, like doesn't have societies. Okay, so 1 person. Final question. How many think that there is intelligent life out there that is beyond what we know? They're smarter than us. Okay, so now Eric's saying, Io's putting X out there. I don't know what that means. But Eric's saying, yeah, I think that I tend to think that there are, maybe I'm just being optimistic, but I feel like there are planets. There's so many billions of them, that there's planets out there where there is not just life, but it's evolved to the point that they are, like, for instance, we detected selenium in the atmosphere of one of these exoplanets. Now, why is that important? Because selenium is only man-made. You can't make selenium. Selenium's not made in nature. So it's a byproduct of technology. So we've detected selenium with spectrum analysis. We detected selenium signature in an atmosphere. Well, that tells me that they probably have some type of technology. They're smelting or something. I don't know if they're at our level yet, but I'm hoping, I guess I hope somebody will give us an answer someday. and they'll come around and solve all our problems. But like we said earlier, they'll probably come around and eat us, or they'll at least take all our lithium. All right. So back to work here. First thing we got to do, well, let's draw a little drawing here. We have their planet, okay, and then we have a moon out here. And the D, that D is between the centers, okay? Sometimes they use R, but we'll use D here. And then we have, we're trying to find the mass of the moon. We'll call that M1, call the mass of the planet M2. Of course, G is there. There's an attractive force between them of 88 giganewtons. So these are 88 gigatons. It's holding the moon into the planet. And by the way, we just touched on the surface of this. I'm going to go into this in more depth with some accompanying media stuff in June, and talking more about gravity, bringing in more Newton stuff, bringing in more of the controversies involved here, Cavendish. This is sort of a, surface talk here. All right, so M1, M2, and then we're saying, well, how much, what is M1? What is the mass of the moon? Okay, so for simple thoughts, we already that's where you kind of come up with your equation, but we already gave us an equation. So G M1 M2 over D squared, that's all you got to do there. And then we're trying to isolate. Now I'm grading this problem right now on the, I graded one problem at a time. I'm grading your unit analysis problem on the test. And still the number one problem students have on unit analysis, they can't isolate a variable. I probably have, out of my 75 students, I probably have 20 that still cannot isolate a variable. It's the same problem they had in August, they still have in May. And I've given you lots of examples, but you're just going to sit down. It's something where you're going to have to go sit down and just work on it and keep practicing isolating variables. We've stopped learning how to do that, and I blame education, but anyway. So we got to get the M1 by itself. And so we multiply both sides by D squared. We have then the force of gravity times D squared. And then we're going to divide both sides by G, big G. When you say G, I use little g for gravity, acceleration due to gravity. I use big G for universal gravitational constant, and M2. Okay. So now what I want you to do, I'm going to put pause. I sent them to the board at this point, and they had to fill this part out. We did this part in class, and the rest is homework, but we got that first part done. So go ahead and work on this. I'll put it on pause. And yeah, it's true. Brandon said, well, it's hard to speculate about life on other planets when we're having a hard time right now. That's an excellent point. He's saying right now we're having this huge debate on what is life. When does life begin? If the whole abortion thing, the whole fetus, when does life begin? When do you say it's alive? I mean, in the zygote stage, when you have a detectable heartbeat, when that's I'm not going to get into that, but you're right. Defining.
I mean, that's not what I was saying, but that works too. Yeah.
Oh, it wasn't. I thought the point you were making. Were you saying that even on an amoeba scale or a virus or even on that scale?
I mean, I remember in biology, we did this whole thing where we were trying to define what life was. Even if you look it up, it's really hard to find a true definition as to what life means. Is it sentience? Is it consciousness?
Yes.
How do you detect that?
Yes. Well, and I think it does apply then to the whole abortion debate, because when does that fetus become sentient? But that's good. That's a very good philosophical debate. But and I suppose we'd have to have it once we finally decide, oh, this planet has life. This planet has just an amoeba, but we're not going to call that life. How about this? How about life starts when that can start to evolve? Like when it can start, because once the evolution process starts, if they have the raw materials, life's going to find a way. I don't know. Okay. So, and back to the physics here. I'll get myself in trouble if I start talking about that stuff. All right. So I'm going to put pause right now, and you keep working. and then we'll come back and we'll finish this part up, and then we'll let you do the rest on your own. Pause record. All right, so kind of glance up here if you can busy working on your paper, but I'll do what I would do. And I apologize, there's never enough room here. So FG, we have 88 giganewtons. 88, it takes 88 billion newtons for this planet to hold this moon, as Newton would say, in its orb. So Newton came up with this too, looking at the moon and looking at the moon cycles and all that. And the apple fell. And then he said, hey, the same force that brings the apple to the ground holds the moon in its orb. And he calculated how much the Earth takes to keep our moon in its orb. I forget the exact number. But for this one, it's 88 giganewtons. The D was 210,000 miles. That's comparable to our moon. It's in the same range. We're like 200,000 kilometers, somewhere like that. This is 210,000 miles. We have and square that. We have a 1 squared. That's okay. Back to this life and other planets. There's a book I have that I'm going to give away now. I'm trying to give away it in class, and it's something about why do we have one moon? We didn't have a moon, something like that. But the moon is crucial. Us having one large moon allowed us to have tidal pools, allowed us to a lot of things to evolve. But the Earth didn't used to have a moon. The Earth had a ring. We were like Saturn. The Earth had its ring, because when that Mars-like object collided, which is called Orpheus, it was another Earth-like planet. When they collided with Earth and wiped, it was still forming, okay, but that coalesced into a ring pattern outside of Earth. That ring pattern, then a woman did a study about 5 years ago, and she proved that ring pattern turned into 2 moons. So the Earth had 2 moons for a while, then those coalesced into 1 moon. But having a moon, not many planets have a moon as large as ours, or where it dominates. We have 1 moon, and it's huge. Like Mars has Charon, but Pluto has Charon, but that's more of a binary system. So, because they sort of orbit around a barycenter between them. Whereas the moon doesn't orbit around the center of the Earth. The moon orbits around a barycenter. Barycenters are the orbit, or the centers of rotation. It's about 1,000 kilometers inside the Earth from the surface down. So we wobble. Part of the reason why we wobble is the moon going around us. But if we didn't have that moon at that right distance, and that's something else we talked about in class, somebody brings up the fact that, well, look, isn't that any evidence of an intelligent designer? The intelligent designers, and I know people that are very smart that are intelligent designers, saying that has to be a God, because how else, the blind watchmaker. But the idea is that the moon's the perfect distance away from the Earth to cause a perfect eclipse, right? And why is that way? And that kind of convinced me when I was a kid. I said, oh yeah, someone said that in church once. Oh wow, there's a God, woo! But it turns out that the moon is getting further and further away from the Earth. Most orbits decay. Oh, that's what we did talk about. Oh, I knew we were way ahead of time. Hold on. Okay, let's wrap this up, and then we got to talk about something. I'm sorry, I forgot about this. Daggone it. Okay, so let's get this in there. Shoot. 1 over, now I got to rush. 6.67. Hold on. 6.67 times 10 to the negative 11th. Then you have these weird units. Newton dot meter squared. And then you flipped it, so the kilogram squared's on top. And then 1 over the mass is of that planet's 9.325. So 1 over 9.3 times 10 to the 25th kilograms and it looks like some kilograms are already going to cancel. And then you just go through and end up in whatever, teragrams, TGs. Okay, but let's get back to, so that finish that up. But let's get back to what so when you ask Newton why do things attract each other, he didn't know. At some point you say, well, God, okay. So Einstein, though, with his theory of space-time, if you talk about empty space, and we also talked about Vera Rubin in class, but she studied this kind of stuff. But if you, if we have space-time, how much time do I got? 1 minute. Ha! We'll talk about this more tomorrow. But then we talked about gravity wells in class. Like the Earth is in a gravity well. These are called gravity wells. I may go 1 minute over, I'm sorry. This is a gravity well, where space-time is bent around massive objects. And then the moon is in a gravity well itself. But that gravity well is orbiting our gravity well. Here's the moon. Hold on, I'm almost done. I'm just going to throw this last little bit up there. So the moon, and I got a better picture of this I'll show you. The moon is out there and it's orbiting us. And I put this bowl and I make this marble go round and round. So the moon's, but then wait a minute, we're in another gravity well. We're in the sun's gravity well. So we put another gravity well in here, and there's our sun. It's also curving space-time down to it. And then here's the question, is the sun in a gravity well itself? What do you think?
Yes, because of
right,
the Milky Galaxy.
Right. So there's a supermassive black hole in the center of the Milky Way. And there it is. So there's this supermassive black hole in the center of the Milky Way, and the sun's in that gravity well. So the moon is in a well, which is in a well, which is in a well. And then a woman named Vera Rubin, we talked about that in class. A woman named Vera Rubin just died a few years ago, but she went out to study this. What then does our galaxy orbit? What gravity well is our galaxy in? And she found out that we make our own, but we're not associated with another one. We're not orbiting anything. And she's also, that led to the understanding, or starting to understand, dark energy. Okay, and the reason I bring that up is a student painted her for the ceiling tile. All right, which I'll put a picture of up. Okay, went over, sorry, because I messed up. We'll talk, we got talking about life and everything else. So I will stop sharing there, and anybody has a question, stick around. Otherwise, the homework is number 4, finish number 5, and then knock off those 2 true false. 6 4s due eventually.